More Laplace transforms. So we've got our definition. Got our definition here of the Laplace transform of a function. If we transform the function, a function of time, we get a function of s, capital F in the Laplace world. And to transform any function, we just integrate from 0 to infinity e to the minus st times that function. We integrate out the dt. We've been building a chart. We've got the transforms of a few functions, a constant function, t, e to the at, the transform of derivative. We've been building this chart. Let's try to add to these. We'll try to prove some of the more additional transforms that we need. Let's do that. Let's take the transform of t squared. We have the transform of t. The transform of t is 1 over s squared. What's the transform of t squared? Well, we pop it into the definition. The Laplace transform of t squared would be integrate from 0 to infinity e to the minus st times t squared. All we have to do is do this integration, evaluate that integration. And we're going to do that integration by parts. So I need one part to differentiate, the t squared. And I need one part to integrate, so let's integrate the e to the s squared. So f prime is going to be equal to 2t, and g is going to be equal to, I'm integrating this e to the minus st, I'm integrating it with respect to t. So that's going to equal to f times g minus the integral of the two things I made. So that's going to be 2t and this piece here. Okay, so now I just have to do this integration. This second integration, if I were to do it, would have to be integration by parts. Oh, and we need to evaluate this. Sub in the top minus sub in the bottom. We have to sub in infinity minus sub in 0. We remember from before that when I sub in infinity, so this piece here, let's look at this piece here. When I sub in infinity, I get 0, e to the minus infinity, infinity squared, the e to the minus infinity is stronger, it drags that to 0, minus, when I sub in 0, I get 0. 0 squared times e to the 0, 0 squared times 1. So this whole bracketed piece disappears. This second piece, well, I could do that integration. I'd have to do integration by parts, but let's clean this up a little bit. I can take this minus s to the outside, because it's a constant with respect to t, and I can take that t to the or that 2 to the outside. Undo. So when I do that, I could still do this piece here by integration by parts, but I don't think I have to. This bracketed piece, by definition, is the Laplace transform of t, and I already know what the Laplace transform of t is. It's 1 over s squared. So this should equal to and I'm going to replace the Laplace transform of t with the 1 over s squared. And so we get 2 over s cubed as the Laplace transform of t squared. So we can add this to the chart. I'm going to put it in under here. The Laplace transform of t squared is equal to 2 over s cubed. So I start to see a pattern here, right? T, s squared, s cubed, t to the 0, I guess, no t, s to the 1. So it looks like the power of s, the power of the s on the bottom is just 1 more than the power of the t. I still have to think about this 1 and this 2. It's going to be factorial. That's 1 factorial, 2 factorial. So here's what I'm going to end up proving then. I want to prove that the Laplace transform of t to the n is n factorial over s to the n plus 1. We've got it proven already for t equals 1 and t equals 2. Okay, up, down, up, down. We're going to prove this by induction. So a proof by induction has 3 parts to it. The first part is I need to show that this formula works for low numbers. And I've got that. It works for 1, it works for 2. So when n is equal to 1, this formula is true. The second part of a proof by induction is I assume that it works for n equals k. So I'm assuming that the transform of t to the k is k factorial s to the k plus 1. The third part of a proof by induction is I show that it works for n equals k plus 1, the next number. So I'm going to have then, if it works for k, then it's going to work for k plus 1. So I need to show that the Laplace transform of t to the k plus 1 is equal to this formula where n is equal to k plus 1. So now I'm transforming t to the k plus 1. Now I'm popping it into definition, and this I'm going to do by parts. So I need one part to differentiate, and that's going to be the t to the k plus 1. And I need one part to integrate, and that's going to be the e to the minus st. This looks like what we did up here, because it is. So f prime is going to be equal to k plus 1 comes down, subtract 1 from the exponent, so that'll just be t to the k. Integrating, well, the integration is going to be the same, so I'm just going to copy and paste right here. So now this is going to equal to f times g. I'm putting the parts in. F times g. Of course, I still have to go sub in the top minus sub in the bottom, minus the integral of the two things I made. So minus the integral of the two things I made. I can steal from up there because the process will be the same. So there's the g, and I just need this f prime. Now, just like what happened in the t squared case, when I sub in infinity here, I get 0. When I sub in 0 here, I get 0. So that's just going to be 0 minus this integral. But I can take the k plus 1 outside, and I can take the minus s outside, just like I did in the t squared case. So I'm going to get the k plus 1, and the minus s comes out front, so this becomes a plus. And so this bracketed piece is the not yet. I did the exact same thing. This bracketed piece then is the transform of t to the k, which from the step up here we assumed was equal to this. And so when I clean that up, I'm going to get k plus 1 times k factorial. That's k plus 1 factorial. S times s to the k plus 1 is going to be k plus 2. And so now we've proven the thing that we want to prove, so I can say Therefore, QED, or by induction, let's go by induction. By induction what? Well, by induction, the transform of t to the n. So I've got this formula. The transform of t to the n is n to the factorial over s to the n plus 1. So we can add this to our chart. So now I can transform t to the any power. Since we can transform t to the any power, we can now transform any polynomial. Because a polynomial is just going to be a linear combination of t to some powers. What about transforming sine to the b, or sine bt? This is our first trig transformation. All right, we'll go back up to here. By definition, that means we can just do this integral. Okay, right away, let's stop for a second here, because if I do this integral, this is the brute force way of approaching this problem. If I do this integral, then I'm going to have to do integration by parts twice. It's totally possible to do that. But since we just figured out that we could take the transform of any polynomial, let's use that information. Let's express sine of bt as its Maclaurin expansion. So here's the Maclaurin expansion of sine of bt. We've just written it out. It's all the odd powers because sine is an odd function. But really the nice thing about that is we've now turned sine into a polynomial. So if I want to take the Laplace of sine of bt, I'm just taking the Laplace of this polynomial. So expanding this out before cubing both sides. Now it's a number times t, a number t cubed, a number t to the fifth. And if I take the Laplace of both sides, I get the Laplace of bt. I guess this b can come out front. Now it's just a Laplace of t, the Laplace of t cubed here, the Laplace of t to the fifth. I need that piece in there. So plus the Laplace of, so this constant times the Laplace of t to the fifth. And again, we just made our formula for the Laplace of t to the 7. So now, what is that? That's b times the Laplace of t to 1 over s squared minus the Laplace of t cubed, that's 3 factorial over s to the 4th plus the Laplace of t to the 5th is going to be 5 factorial over s to the 6th (7 factorial over s to the 8th dot dot dot). Now the nice thing is that all of these 3 factorial cancel, 5 factorial, all of these cancel. So let's cancel those out. There's no more t's here. There's no more t's there. 5 factorials cancel. I can write this as one fraction. The 7 factorials cancel. And I can write this as one fraction. All right. But now I see that, let's put the b up top here then. This looks like a geometric series. Cube, 5577. Yeah. Now, geometric series, where the first term is b over s squared, and this, the next term is just the last term times I multiply by b squared on the top and s squared on the bottom. So it's a geometric series. It's a geometric series where the first term is equal to and the ratio, 1 minus the ratio is b squared over s squared. Well, no, minus that. So I'm thinking of the rules for a geometric series. A series of a plus ar plus ar squared plus ar cubed plus ar to the fourth, blah, 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 on to forever is equal to a over 1 minus r. Take a look at the blue box. So now I've got the, oh, I guess we're good. There's the Laplace of sine b to the t. Well, we can clean that up. Let's multiply top and bottom by s squared. So there'll be a b, that'll be s squared plus b squared. So there's our Laplace transform of sine b to the t, and we didn't do any integration. So that's a nice thing. We can put that into our chart. So if I want to take the Laplace transform of sine 3 to the t, that's just going to be equal to, the b is 3, so then s squared plus 9. Done. Just using our rule. No integration, just using the chart. Okay, let's do one more problem, or let's do one more derivation. Let's make the cosine. Now we get choices. What we could do is we could put the cos bt into the definition. Well, we didn't do that. We avoided that. We could have done that up here. We took the Laplace transform of sine. We'd have to do integration by parts twice. Or we could write sine of bt equal to its Maclaurin expansion, and then transform it like we did transforming a polynomial, then use geometric series. We could do that as well. But we could even do this easier, because I know that the if f is equal to sine of bt, then f prime is equal to b cos bt. So I'm going to take the transform of b cos bt. Well, that b is a constant, so it can come outside. That b is a constant, so it comes outside. And now I'm transforming, well, I've got the derivative, right? I can use this, I can use my differentiate. If I Laplace the y prime, it's s times the Laplace of y. So that's going to be s times the Laplace of sine bt plus f naught. Well, sine of 0 is 0. I'll write it in there, but it's gone in a second. Now I've got then b cos b times the Laplace of cos bt is equal to s times the Laplace of sine bt I have. That's this piece. I can cancel b off both sides. Cancel b off both sides. That's a 1. And I can just put that s on top, I guess. So now I've got the Laplace of cosine bt. I can add that to my chart. So we transform that with just using our derivative rule. As promised, the bigger chart we get, the more of these tools we have to work with, the less actual integration that I have to do. All right, let's finish up by doing an example. We've got all these rules. Let's, I want to focus back on what we're trying to do. We're using Laplace transforms to solve a differential equation. So let's solve this differential equation. First thing I'm going to do is Laplace of both sides. The Laplace of y prime, sy minus y naught. That's using this rule here. Equals minus 2 times the Laplace of y, the unknown function, plus 4 times the Laplace of t. The Laplace of t is 1 over s squared. All right, now I'm in the Laplace world. The next part is solve for y. So when I solve for y, bring this piece over to the other side, factor out a y equals 4 over s squared. Solve for y. Next I want to do partial fractions and break this piece up because I want to unlaplace this, but I could unlaplace a number over s plus 2. I could unlaplace a number over s squared, but I can't unlaplace the product of this. So we break it up into pieces. Partial fractions. Nice. Now let's unlaplace. Capital Y of s unlaplaces to be little y of t. 1 over s plus 2. That's our e to the minus 2t. 1 over s. 1. 2 over s squared. 2t. There's our solution to this differential equation. Let's check. If I make t equal to 0, I do get y equal to 0. It does go through the origin like it's supposed to. Normally, we would have solved this with as a y prime plus py equals q as a first order linear, but we can now solve it with Laplace.